This is lecture 30, and in this lecture we are going to be talking about heat capacity. So we'll start this lecture off with a bit of a quandary. All right, let's say it's summer, you're 8 years old, and your mom's taking you to the pool. She lets you go barefoot because that's the only time your mom lets you go barefoot out of the house, right? And so you get to the pool and you step out of your car onto the hot asphalt and it burns, it sears your feet so bad. So you know you have to run. You have to run and get onto the grass. That's your lifeline. When you get on the grass, it's cooler, it doesn't burn your feet, and you're able to walk, right? Well, what's going on here? So if we actually plot the temperature of the asphalt and the grass throughout the day, you'll notice the black line here is the asphalt. We got the time of the day on the bottom, and then the temperature in degrees Celsius on the y-axis. And as we go throughout the day, the asphalt actually gets hotter than the grass does throughout the day. Even though they've both been in the sun all day, in the same sunlight, right next to each other, what's going on? Why is the asphalt getting so much hotter than the grass? Well, the answer is heat capacity. So heat capacity can be thought of as how much heat can a material hold before its temperature rises. And it turns out that every material has a different heat capacity. So the same amount of heat that will heat the metal on your car is a lot different than the heat that's required to heat up the grass on the field. So heat capacity is defined as the amount of energy needed to raise the temperature of an object by 1 degrees Celsius. So if we want to figure out how much heat is actually required to raise the temperature of something by some amount, we'd use this equation, where again, Q is our heat, C is our heat capacity, and delta T is our change in temperature. Now there are actually different versions of heat capacity. So this version that we're looking at right here is the quantity of energy needed to raise the temperature of an object by 1 degree Celsius. So if we're raising the temperature of an object, that could be a ball, that could be a car, that could be a person, right? It's the amount of energy needed to raise that thing's temperature by 1 degree Celsius. But in chemistry, we're often dealing with moles of things, right? We don't care about specific objects. We're going to ask, if I have 5 moles of helium, how much heat do I have to put in to heat that helium? So for a problem like that, we'll turn to what's called the molar heat capacity. So the molar heat capacity, you'll notice, has a lowercase c, and at the end of this CP thing, there's a comma n right there. Sometimes that n is there, sometimes it's not. But this molar heat capacity then relates our heat needed to raise an object by some temperature based on how many moles we have. So the equation for the molar heat capacity is different. So in this case, heat equals the number of moles times the molar heat capacity times delta T. So if I have 5 moles, for example, I can multiply that by the heat capacity of a single mole, and now I know how much heat I have to put in to raise the temperature of 5 moles. Now the last type of heat capacity we use is what's called the specific heat capacity. So this is the quantity of energy needed to raise the temperature of 1 gram by 1 degrees Celsius. So this heat capacity has a lowercase s in its subscript as well. So in this case, the equation for heat is Q equals m, which is the mass, times the specific heat capacity times delta T, right? So in this case, if you're dealing with 10 grams of iron, you want to know how much you have to heat it up by, you can use the specific heat capacity, and that lets you not have to convert into moles. Now, a number that you should know is the specific heat capacity of water, which is 1 calorie. So the specific heat of water is 1 calorie per degree Celsius, right? So this is how we actually define the calorie scale, is based on the specific heat of water. Now, when you're using these different specific heats, pay attention to the units. Because in my case, I've included all the appropriate subscripts on these constants, but many tables don't. Many tables will just say heat capacity, or not indicate whether it's molar or specific. So in that case, you need to look at the units that are on it, right? A Molar heat capacity will list in units of joules per mole degree Celsius. Heat capacity will just list in joules per degree Celsius. And specific heat will list usually in joules per degrees or per gram per degree Celsius. Let's see if you understand this concept real fast. So let's say the same quantity of thermal energy is added to equal masses of 4 metals: aluminum, copper, iron, and titanium. All of these metals are initially at the same temperature. Which metal has the highest final temperature? Okay, so just to reiterate, we've got 4 pieces of metal, different types. We have the same mass of each, and I want to know if I give the same amount of heat to each, which one is going to get the hottest. I've got their heat capacities listed right here. You can try and figure out which type of heat capacity that is. Go ahead and pause the video now and try and figure this out. All right, well, if we look at these heat capacities, aluminum has the highest at 0.897 joules per grams per degree Celsius. So this is its specific heat because it's in grams. So aluminum has the highest specific heat, and then copper has the lowest specific heat. Now, since we're dealing with equal masses here, and we have the specific heat, we're in good shape. We don't have to worry about converting any of these to moles or anything like that. Aluminum has the highest heat capacity here at 0.897. Copper has the lowest at 0.385. Iron and titanium are both in the middle there. So if I put the same amount of heat in each of these, which is going to get hotter faster? Well, for aluminum, having a high heat capacity means that if I put a lot of heat into it, the temperature just raises a little bit. Whereas with copper, with a low heat capacity, what that means is that if I put a little bit of heat in, the temperature changes more quickly. Okay, so the idea is a higher heat capacity means slower rise in temperature because it can store more heat in it. So the answer here is going to be copper, because copper is going to be the metal that has the highest final temperature, has the lowest heat capacity, highest increase in temperature here. Let's look at an example of another specific heat problem. At an elevation where the boiling point of water is 93 degrees Celsius, and you have 1.33 kilograms of water at 30 degrees Celsius, and it's going to absorb 290 kilojoules from a mountain climber's stove before it runs out of fuel. Was this amount of thermal energy sufficient to heat the water to its boiling point? How would we solve a problem like this? Well, we turn to the equation Q equals mc delta T. Now, why did I choose the specific heat equation? Well, because it listed my water in grams, in this case kilograms, but still grams. So I could have gone with the molar heat capacity, Q equals NC delta T, right? But why go through the trouble of converting into moles if I don't have to? So I will have my mass here of 1.33 kilograms. I have my heat capacity, which I don't really have written down on here, but we can remember it. And my delta T is just going to be equal to my final temperature minus my initial. So with my mass, I always want to convert this into grams. Why? Because specific heats are always listed in grams. They're almost never listed in kilograms. So always convert your mass into grams. For the specific heat, like I say, it's not written up here, but I do actually know the specific heat of water. So the specific heat of water is 1 calorie. Now in this case, I might want to convert to joules since the amount of energy I absorbed from the sun is in joules, so it makes sense to be able to compare those directly. So I could either convert my calories into joules, or I could go from joules to calories. It's kind of your choice, and it depends on what the question is asking specifically. So if I know my heat capacity is 1, I can look on the equation sheet to convert between calories and joules, and it might also be helpful just to know this number, 4.184. So 4.184 joules is equal to 1 lowercase calorie. And if you can just remember that number, it'll make your life a lot more streamlined. So the heat capacity of water in joules is 4.184 joules per gram degree Celsius. And my delta T I'm trying to go from 93, or sorry, from 30 degrees Celsius to 93. So that would be a delta T of 63. Now I can plug these numbers in. I've got my mass, I've got my heat capacity, I've got my temperature. I multiply those all together, and I find that I'll need 350,000 joules, or 350 kilojoules of energy, to go from 30 degrees to 60 or to 93. So was 290 kilojoules enough energy? No, we're going to fall a bit short with that amount of energy. So now I'm going to give you a similar practice problem, and we'll see how you do with this. In this problem, we're going to say at the elevation where the boiling point of water is 93 degrees Celsius, you've still got your 1.33 kilograms, you're still starting at 30 degrees Celsius, and you're still absorbing 290 kilojoules, but this time I want you to tell me what the final temperature of the water is. And I have the equation here that you'll need to solve this. Go ahead and pause the video now and try and figure this out. Okay, all we need to do here is solve for our final temperature. So a lot of these heat capacity problems are going to be highly algebra based, right? So we're going to solve for that by dividing over my MC. So when I divide over MC, I'll get T final equals Q over MC. But then I'll also have my T initial to deal with. So I'll have to add that T initial over there too. So T final will be equal to Q over MC plus my T initial. I don't know why I and I right there is big, but it is for some reason. All right, so then I have my heat that's coming in, 290 kilojoules. I'll generally want to convert that into joules when I'm dealing with heat capacities, because heat capacities are generally listed either in joules or in calories. So the joules then can cancel out. I'll need to convert my mass from kilograms to grams. But then once I do that, add all this together, I'm going to find that my final temperature is 82 degrees Celsius. All right, so this is when we're heating a material. But what happens when we go through a phase transition? Let's start this conversation out by asking a question. Can liquid water ever get hotter than its boiling point? The answer is no, it can't. So you can change the boiling point by changing your pressure, or also by adding salt to your water. But if the boiling point is set, you can't get water to be hotter than that. So let's say you've got a pot of water boiling on the stovetop. The stovetop is continually adding energy in. But once the water gets to its boiling point, which is about 95 degrees Celsius here in Provo, so once it's at 95 degrees Celsius, the temperature stops changing in the water. So what's happening to all the heat that's going in there, right? Where is it going? Well, the answer is it takes heat to convert between phase transitions. We talked a little about this in the last lecture. Now we'll get formal in terms of math. So for example, if I'm going from ice to liquid water, in ice, I have all of my water molecules stuck together in a specific arrangement. To overcome that arrangement, I have to put heat into this so that my molecules can overcome those strong intermolecular forces. That doesn't mean I'm actually increasing my kinetic energy. In fact, my kinetic energy after I'm melted is the exact same as before I melted, right? I'm still at the same temperature of 0 degrees Celsius. Now, if I keep heating beyond that, I can increase my kinetic energy, but not right at the melting point. So the idea here is that ice is going to take some amount of heat, specifically what we call the heat of fusion, in order to turn into liquid water. So the formal equation here for figuring out how much heat you have to put in there for fusion is as follows. So the heat is equal to the number of moles times the specific heat of fusion. So Q in this case will be equaling N, the number of moles, times the delta H of fusion for 1 mole. As we learned in the last lecture, our delta H here can be equal to our heat. So this is just the amount of heat we have to put in. The last time we talked a little about these delta H's of transitions too. So if I'm going from liquid water to liquid vapor, right, I'm going to have a delta H of vaporization If I'm going from water vapor to liquid water, I'll have a delta H of condensation. Similarly, if I'm going from ice to liquid water, that would be my delta H of fusion. I'm not entirely sure why going from fusion or going from a solid to a liquid is fusion, but for some reason it is, and it's a historical reason. And then going from a liquid to a solid is going to be my delta H of solidification. There's also delta H's of sublimation and deposition. We don't usually worry about those a ton because most of the time we're dealing with things turning into liquids. All right, but if I'm going from a liquid to a gas, I'll have one delta H. If I'm going in the opposite direction, I'll have an equal but opposite delta H, right? So my delta H of vaporization is equal to the negative of my delta H of condensation. Now, how does this factor into a heating problem? Well, let's do a problem first where we just look at a phase transition. Let's say during a strenuous workout, an athlete generates 233 kilojoules of thermal energy. Knowing that the delta H of vaporization is 40.7 kilojoules per mole for liquid water, which is the sweat on the man's forehead or the woman, what mass of water would have to evaporate from the athlete's skin to dissipate this energy? Well, we'll turn to our equation here. Our heat is equal to the number of moles times the delta H of vaporization. Now in this case, we have our delta H of vaporization. It's 40.7. We actually already have our heat too, which is 233 kilojoules. So we need to solve for the number of moles. So that would just be N equals Q over delta H. So then we can just throw in our Q value, which is 233 kilojoules, and our delta H value, which is 40.7 kilojoules per mole. And here I'll make a point that often heat capacities, the value denoted by a C, are listed in joules or calories, but our delta H's are generally listed in kilojoules. Okay, so be really careful to look at what units of everything you're working with. Units are a great place to screw up and cost yourself points. But if we do this, do our Q divided by delta H, we'll find that we need 5.72 moles of water, which is equal to 103 grams of water, which is also equal to about a half a cup of water. Right, so this person's sweating quite a bit, and that's evaporating to cool them off. Now let's combine a phase transition with heating an object up to that phase transition. Let's say you're camping in the winter and want to make 1 cup of hot cocoa using 250 grams of clean snow as your water source. How much heat do you need if you want the water to be 98 degrees Celsius when you stir in your cocoa? Okay, so we've taken a bunch of snow. It's starting at negative 20 degrees Celsius. Let's figure out exactly what happens here by looking at what we call a heating curve. So on a heating curve, what we have is heat on the x-axis and temperature on the y-axis. So if we're starting at negative 20 degrees Celsius, we're going to be a solid at that temperature. And so while we're a solid, we will heat up until we get to our melting point. And during this range where we're a solid, our heat equation will be Q equals MC delta T. But then we get to this phase transition where we got to go from a solid to a liquid. That phase transition is going to take some amount of energy. And that energy will be expressed in heat as Q equals N delta H of fusion, right? So that is our heat required to melt the ice. Then once we're melted, we'll need another equation to describe the heating of the liquid. That'll be again Q equals MC delta T with our specific heat there. Then if we get up to our phase transition between a liquid and gas, we'd have to use another equation there. And then if we were heating the gas, we'd have a fifth equation for heating the gas. Now luckily, in our problem, we're only going up to 98 degrees Celsius, which is right here, right below our phase transition. So we're only going to be dealing with heating the solid, melting the solid, and then heating the liquid. Right, so our total heat is going to be a combination of all these equations. So our total heat Q is going to be equal to the mass of the ice times the specific heat of the ice times the change in temperature of the ice, plus the number of moles of ice times the delta H of fusion for ice, plus the mass of our liquid water that we've generated, plus our specific heat of that water, plus the change in temperature the water undergoes. So what we'll need for this problem is specific heats. We'll also need our delta H of fusion. I'm going to point out real fast that the specific heat of the solid ice is different than the specific heat of the liquid water. Okay, ice actually has a heat capacity of about 50% of that of liquid water, which means it's easier to heat up ice than it is to heat up water. And I'll also point out that the heat capacities, I pointed this out before, but I'll do it again. The heat capacities here are both listed in joules, whereas the delta H of fusion is listed in kilojoules. All right, and that's an important point to keep straight while you're doing this. Now I'm going to actually break this back into separate parts and solve each of these independently, just so you can see a lot of the detail that I'm doing here. All right, so my heat for my solid is just going to be equal to my mass of my solid times this heat capacity of my solid times my delta T. But what is my delta T here? Am I going from negative 20 degrees Celsius to 98 degrees Celsius? Well, not for my solid. That's the overall temperature change, but my solid is only a solid to 0 degrees Celsius. So my delta T for my solid is just negative 20 to 0, or in other words, 0 minus negative 20, which would be 20. So I'll multiply that out and get 10,550 joules to warm the snow. I'll then calculate my heat for this phase transition. So my Q is equal to the number of moles times my delta H of fusion. In this case, I have to take my 250 grams here and turn it into moles. So I'll divide by the molecular weight of water, and then I'll multiply by my delta H of fusion here, which is 6.01 kilojoules per mole. I'll multiply that out, find that I need 83.38 kilojoules to melt the snow. Okay, now I've got it into a liquid phase. Now I've got to heat the liquid up to 98. So for that, I've got my heat equaling my mass times my specific heat times my delta T again. Here I've still got 250 grams, right? Conservation of mass says that if I change between a solid and a liquid, I still have the same mass. Then I times it by my heat capacity of the liquid water times my delta T of the liquid water. Again, what is my delta T for liquid water? Well, it's only a liquid between 0 and 98 degrees Celsius in this problem, right? It's not a liquid below 0 degrees Celsius. And yes, it's technically a liquid up to 100 degrees Celsius, but we're only going up to 98 degrees in this problem. So I can then take all of these heats and add them together. I've got about 10 kilojoules from heating the solid. I've got about 84 kilojoules from from that phase transition, and then about 102 kilojoules for heating the liquid. So in total, this is going to take 196 kilojoules of energy. Let me give you a problem to see how you're doing with this. In the heating curve for water that I have shown below, the slope of the solid only heating line, segment AB, so that's just this line right here between A and B, is noticeably steeper than the slope of the liquid only heating line, which is between C and D, right here. Why? Go ahead and look at these options, pause the video and try and figure this out. Well, there's actually two statements on this that are true. So on a good heating curve, you should be able to figure out the delta H of fusion and the delta H of vaporization by looking at how long these lines are. Now, if I look at these, the delta H of vaporization has a much longer line than the delta H of fusion. So we can say that the delta H of vaporization is larger than the delta H of fusion. But that has very little to do with the actual problem. The problem is actually asking about these slopey lines here, right? So if ice has a steeper slope, if I add a little bit of energy, I get a lot of temperature increase. A little energy, a lot of temperature. With water, if it's got a steeper slope, a little bit of energy, a little bit of temperature increase. A little bit of energy, a little bit of temperature increase. So the reason the slope between A and B is so much steeper than the slope between C and D is because ice has a lower heat capacity than water, okay? And so it's just going to heat up faster. So we're going to be calculating heat in a lot of different contexts, right? So we'll have heating an object, which would just be Q equals C delta T. So you'd have the heat capacity of a specific object. You can also be heating a certain number of moles of some pure substance, and then your equation is Q equals NC delta T. You could be heating the mass of something, then it would be Q equals MC delta T, right? Notice that these heat capacities all look different. For heating an object, you have a capital C. Heating a pure substance or a certain number of moles or grams, you have a lowercase c, and you have different subscripts for those. But those subscripts and even the capitalization are often incorrect in technical usage. So, meaning that people often write them wrong when they're writing these things out. So always make sure to look at the units of your heat capacity that you're using. The units on it will tell you which kind of heat capacity it is. If we're going through a phase transition, such as melting a solid or vaporizing a liquid, our equation will be Q equals N delta H. And then we'll pick the delta H associated with the phase transition we're interested in. Now, you won't find any heat capacities or delta H's on an equation sheet because they are not generalizable at all. Every substance, every material has its own heat capacities and its own delta H values. So if you were going to have a problem about these on an exam, the problem would have to provide the heat capacities and the delta H values, either in a table or somewhere in the text. All right, so you could get a problem that looks like this. Let's say we're trying to recycle aluminum cans. To recycle aluminum cans, the aluminum is heated from room temperature, 25 degrees Celsius, to its melting point, 660 degrees Celsius, and then melted so it can be reshaped. If the heat of fusion for aluminum is 10.79 kilojoules per mole, and the molar heat capacity is 24.2 joules per degrees Celsius per mole, how much energy does it take to recycle 1 mole of aluminum, which is about 2 cans? Okay, when you get a problem like this, I actually always recommend drawing out a heat curve. Even if it's a simple heat curve, even if it's wildly out of proportion, I suggest drawing it. So in this case, we're heating from 25 to 660, we're heating that metal, and then we're going through a phase transition, okay? By drawing the diagram, I can put in my mind which steps are happening. So while I'm heating this metal, I'll be using this equation Q equals NC delta T, and while I'm going through a phase transition, I'll be using the equation N delta H. Now you'll notice here I'm using the Q equals NC delta T equation instead of Q equals MC delta T. I'm using NC because I'm looking at 1 mole of aluminum. And why would I switch to my specific heat and use the MC delta T if I'm already in moles? And just save yourself some time. So the total heat that I'm going to have to undergo or give into this aluminum is going to be equal to these two heats added together. So I can substitute these two equations in here, and now I've got my total heat equaling these two equations. And at this point, it's just plugging in numbers, right? I've got 1 mole in for each of these ends. For my heat capacity for my solid, as I'm heating, I am going to actually convert that from joules per degree Celsius per mole to kilojoules per degree Celsius per mole. The reason I'm going to do that is because my phase transition, delta H value, is listed in kilojoules. And if I'm adding two values together, they need to be in the same units. So always try and make sure to match those. You can either do it in kilojoules or in joules. Generally, if it's a question on an exam or a homework problem, you're going to try and match the units that the problem is looking for. All right, then my delta T for this is just 25 to 660, and then I'm just going to have 1 mole times my delta H of fusion here. So I work that math out, and you'll find that this takes about 26.2 kilojoules of energy to go through this process. Now to put that into context, 26.2 kilojoules, if I convert that into food calories, that's uppercase calories. So 1 food calorie is equal to 4.184 kilojoules of energy, right? Because 1 lowercase calorie is equal to 4.184 joules, and 1 uppercase calorie is equal to 1,000 lowercase calories. Anyways, 26.2 kilojoules is equal to 6.26 food calories, which is about 1/3 of what you'd get from eating a green olive. Now let me give you this problem in a slightly different way. let's say we actually already know how much energy it's going to take to recycle 1 mole of aluminum. Let's say we already know it's 26.2. In essence, the aluminum is heated from room temperature to its melting point and then melted so it can be reshaped. If the heat of fusion for aluminum is 10.79 kilojoules per mole, what is the molar heat capacity of aluminum? How would we solve this problem? Well, first, like always, you should draw a diagram. Draw a heating curve. In this heating curve, right, we've got our two equations. We've got our heating of the solid, and we've got our melting of the solid. We also know that our total heat here is going to be equal to 26.2 kilojoules, and our total heat is still going to be equal to these two equations added together, right? So now, if we look at the question, it wants us to find the molar heat capacity of aluminum. That's the CP value. And we can do that. This is just algebra at this point, right? So let's start by solving this just for this expression NC delta T over here. So we'll subtract over this N delta H, do a little rearrangement here. And now we can start plugging in some numbers for everything over here on the right. We can plug in our total heat, our number of moles, and our delta H of fusion. Then we can divide over by N delta T here and find that our heat capacity is equal to 15.4 kilojoules divided by the number of moles and our change in temperature. We know what those are from the question as well, and we can find out that the heat capacity is 24.2 joules per degree Celsius per mole. So the big places that people mess up on are not drawing a heat curve and accurately are figuring out which equations they need to combine, right? If we're going from a solid all the way up to heating a gas, that's going to involve 5 different equations. If we're going from a liquid just to a gas, that would involve heating the liquid, vaporizing the liquid, and heating the gas. That would be 3 equations. If we're just heating a gas from one point to another, that's just going to be 1 equation, right? So it's always a good idea to draw out your heating curve and then use your heating curve to figure out how many equations you're going to have to combine to figure out your total heat in these problems. All right, one last problem, and this will get us set for the next lecture. This is actually how we measure the heat capacity of things. We heat them up and then we put them in water to see how the water changes temperature. Or at least this is one way. We'll talk about a couple ways in the next lecture. So if I take, for example, 20 grams of iron and I heat it up to 1,000 degrees Celsius and then put that iron in 1 liter of water at 25 degrees Celsius, I can figure out how much heat can be stored in that iron. I can figure it out because when these two combine, their final temperatures are going to be the same. These two, the hot iron and the water, are going to equilibrate to the same temperature. So if I can take water that I know the heat capacity of and mix it with something that I've heated that I don't know the heat capacity of, I can see what the final temperature is and use that to solve for my heat capacity of the unknown. I can do that by realizing that the amount of heat lost by my material is equal to the amount of heat gained by my water, right? So if I have a 1,000 degree piece of iron, I put it in water and I do it carefully so there's no splashing, then all of the heat lost by the iron, and iron is going to lose heat, so we'll say it has a negative Q in this case, is going to be gained by the water, so water would have a positive Q. So the negative Q of iron is equal to the positive Q of the water. And then at this point, we know these equations for Q, right? Q, if we're just heating up a liquid or cooling down a solid, is just going to be MC delta T. And we can have one of those equations for each species. We can then plug in, for example, our starting temperatures here. And then if we do that, you'll remember that delta T is just equal to our final temperature minus our initial temperature. Each of these has a different initial temperature, but they should have the same final temperature. All right, we can then rearrange some things here, factor it out so we get just our final temperature values on our right, our initial temperature values on our left, right? To do this, we take MC and multiply it into this stuff in parentheses, and then we rearrange a bit. And then at this point, we can start plugging in numbers. We can factor out T final by itself over here. And then at this point, it's all just algebra. And so from this problem, we can see that the final temperature is actually only 27.09 degrees Celsius. So if you take 20 grams of hot iron and heat it up to 1,000 degrees Celsius, put it into water, it actually doesn't increase the water's temperature that much, just 2 degrees. So you can see how we could do this, and if we knew the mass of our materials really well, and also knew the temperatures of them really well, and we know the heat capacity of water, it wouldn't be hard to do something like this and back out the heat capacity of something else. But that's a discussion for next time when we'll get into calorimetry and talk a little bit about bomb calorimetry.